This is section 13.3, part D. We're now going to start looking at what happens when we have to integrate over a region that's not a polar rectangle. For example, if you look at the picture here, although the theta values go between a constant alpha and a constant beta, the values of the radius, the r values, aren't nice pieces of circles, right? They're more irregular than that. So we're saying it goes from, say, an r equals g of theta to an r equals h of theta. When we set up our double integral of whatever our function f of r and theta is, we'll still use the same dA, r dr d theta. But to set up our limits of integration this time, we'll continue to use the idea of this radial spoke. The picture that I stole here actually already started to put this in. We enter our region here at r equals g of theta, and we exit our region here at h of theta. So always think from the origin out. Where do you start going into your region, and where do you leave the region? That'll give you your limits of integration. The theta values from alpha to beta will still be constant. Again, remember the outer limits of integration must be constant, and so that's important. All right, in the next example 6 has 3 parts. We're going to use the same diagram all 3 times, but I'm going to ask you to shade in different parts of it to represent the region R. So this is my region R1. It's the piece, or the little moon-shaped piece here, that's between the circle r equals 2 and then the circle r equals 4 cosine theta. We'd like to integrate the function 2x dA over that region, R1. I'm going to set up my integral. My equations are already in polar coordinates here, so I definitely want to do this in polar. So let's write this as, pull the 2 out here, r cos theta for x, and then the dA, r dr d theta. All right, as far as the limits of integration are concerned, starting from the origin, I'm going to draw that radial spoke, and I enter my region R1 right here at this circle where r is equal to 2. I exit my region on this circle where r is equal to 4 cos theta. So there are my r limits of integration. For the theta limits, I would need the theta values at those intersection points, and I can get those just by intersecting my 2 curves. As always, we want to set them equal, so set the 2 r values equal. 2 equals 4 cos theta. Dividing by the 4, oops, let's try that again, 1/2 equals cos theta. And then the inverse cosine of 1/2 inverses cancel on this side, and the inverse cosine of 1/2 in the first quadrant is pi over 3. You just get that off of a unit circle. Now, by symmetry, we could tell that this theta value would have to be negative pi over 3 down here in the 4th quadrant. Or the other option is maybe I could just use symmetry on my entire integral. What if I only integrated the top half and then doubled it? Would that give me what I need? I have to check 2 things to use symmetry. First of all, is the region symmetric? And it definitely is. The bottom area down here is exactly the same as the top area there. So far, so good. The other thing I have to be careful about is to make sure that the integrand is the same in both halves of the region. In this case, it is. Any point up here would have a corresponding point down here, and the value of 2x is the same here as it is there, because those points both have the same x value. They don't have the same y value. So if there was a y involved here, I would have been in trouble. However, x is symmetric through this whole thing. So I think I can actually say, what if we just multiply by 2 and then just go from 0 to pi thirds? It's not absolutely necessary to use symmetry, but it's tempting, and sometimes it does save us some work, so I wanted to give us a chance to talk about that here. All right, so we end up with 4 times the integral from 0 to pi thirds. And let me write this out. The integral from 2 to 4 cos theta of r squared cos theta. dr d theta. All right, here's the bad news. We can't use our favorite trick. I have theta in the integrand. I have theta in the limits of integration. This is not all constant with respect to theta. So I'm going to actually have to do both integrals this time. We'll go ahead and do the r integral by hand. So integrating the r squared is going to give me a 1/3 r cubed. I'm going to pull the 1/3 out, put it there with the 4. And this goes from r equals 2 to r equals 4 cos theta. Plugging in the 4 cos theta, I'm going to get, oh, I'm sorry. Let me fix that right now. I said the integral here was 1/3 r cubed, but I actually accidentally put my 1/3 in twice, didn't I? The 1/3 I had already pulled out there, so I don't need it in here anymore. All right, r cubed. That's going to be 64. And then I'll have a boy, I'm not doing very well on this problem. I am so sorry, you guys. Let's go back for just a moment. Right from the beginning, we had our setup okay. Let me walk through this because I see a second mistake that I've made. We did the 2 times 2 is 4. The integral from 0 to 3 and from 2 to 4 cos theta. R times r gave me r squared. I only had cosine theta to the first, not squared there. Let me get rid of it there as well. Sorry about that, making too many videos in a row here. So I integrated 1/3 r cubed. Integrating with respect to r means cosine theta does not change. And then I've got my limits of integration from 2 to 4 cos theta. I think I've got this right now. All right, so there's my 4/3. R cubed. 4 cubed is 64. And then cosine theta is also going to be cubed. And then times the cosine theta that was already there. Minus. Plugging in the 2. 2 cubed is 8. Times that cosine theta. Phew. All right. Ultimately then I have 4/3 times my integral. That'll be 64 cosine to the 4th of theta minus 8 cosine theta d theta. And let's see, I believe I did do this one. Looks like I did it right when I did it for practice. When I did all of that, didn't come out to anything particularly nice, so I multiplied everything in, including the 4/3, and I got 40.439. All right. In the next problem, we're going to have the same diagram, but we're going to integrate over a different part of it. My integrand this time is r squared, and I'd like to use r2 as this shaded piece kind of trapped in between the two circles. And I'm only going to look at the part that's in the first quadrant. So, I go to set up my integral. And once again, I'm going to say, since I've got an equation that's already in polar coordinates, let's change this to polar as well. That would be r sine theta squared. And the dA is r dr d theta. All right, what am I going to use for my limits of integration? I've got a bit more of a problem with this one. If you think about a radial spoke, I would be tempted to say, hey, great, no problem. I can start at 0, and I will. And I exit my region through this circle r equals 2. That's all very well and fine, but it's not true for the entire region. Notice that had I drawn a radial spoke up here, I still would have entered at 0, but this time I would have exited through the circle r equals 4 cos theta. So I'm going to have to set up a second double integral this time. I still have the same integrand. But for the second integral, I start at 0 for my radius, and I go out through r equals 4 cos theta. All right, what about the theta values? Well, everything changes right at that intersection point. And remember, that was theta equals pi thirds. We figured that out in the last problem. So, from 0 to pi thirds, I'm going out through the 2. And then for the rest of the quadrant, from pi thirds to pi halves, I'm exiting through the 4 cos theta. All right, there's 2 integrals that we have to calculate, so I'm going to have to probably write a little bit smaller, but let's get started. In order to do that, I'll take this first one, and that would be r cubed sine squared theta dr d theta and when I integrate that dr, I'm going to get a 1/4 r to the 4th sine squared theta. I just did it again. Holy cow. All right, I promise I'll take a break after this one and stop making mistakes. That r shouldn't have been there. That was r squared times r was already in my r cubed. So integrating r cubed, 1/4 r to the 4th times sine squared theta from r equals 0 to r equals 2 d theta, which gives me 1/4 times the integral. Plugging in the 2, that will be a 16 sine squared theta d theta. That one's to the point where I can finish that on the calculator. Plus the second one, once again, r squared times r is r cubed sine squared theta dr d theta. And same deal. If I integrate that, I'll get a 1/4 r to the 4th, so I'll pull the 1/4 out. R to the 4th sine squared theta from r equals 0 to r equals 4 cos theta d theta. And plugging in r to the 4th, it's going to give me 256 cosine to the 4th of theta times sine squared theta minus 0, and that still has to be integrated d theta. I did both of these integrals on the calculator, and if I did them right, I had 1.228 for the first one and 0.362 for the second, giving me a final answer of 1.59 for that problem. All right, sorry about those errors. See if I can focus enough to do this one last one on example 6. All right, this time we want to integrate the function x plus y. And our region 3 is this little tiny piece here in the first quadrant. So x plus y, that's going to be r cos theta plus r sine theta. dA is r dr d theta. And then I need to figure out my limits of integration. If you imagine, oops, let me get my other color here, a radial spoke here starting from the origin and going out, you can see we enter our region through the 4 cos theta, and we exit through the r equals 2. And that's going to be consistent all the way through. It's going to get really, really skinny over here, but it's the same thing. We're always going to start at the 4 cos theta and stop at the r equals 2. We already knew this intersection point was theta equals pi thirds. So we'll go from pi thirds to the end of the first quadrant, which would be pi halves. All right, I'm going to do a little algebra on this before I start to actually integrate. If I factor the r out of the parentheses and put it with the r out here, that would be an r squared times cos theta plus sine theta. And again, I do have thetas in my integrand, so that no way can I use that nice little trick. I'm going to have to actually work for this one. So let's go ahead and do this. We would get a 1/3 r cubed when we integrate the r. Just have one integral now. Times cos theta plus sine theta. My limits of integration here are still my theta values. And I'm going from r equals 4 cos theta to r equals 2. And let's see here. Plugging in the r equals 2, it's going to make that an 8. Minus, plugging in the 4 cos theta, cubing that is 64 cos cubed theta, times that cos theta plus sine theta. And I have a really big, ugly integral left, so thank goodness for calculators at this point. When I did that one on my calculator, including the 1/3, I got 1.21. All right, there's only one more example, so I know this video is getting a little bit long. I apologize for that, but let's finish up the section and call it a day. In example 7, we're asked to use a double integral to find an area inside the polar curve, r equals 2 cos 4 theta, and outside r equals 1. That's just a circle of radius 1, but unless you have a lot of good memory for polar curves, you may not remember what the 2 cos 4 theta looked like. I've set my calculator to polar mode, so I can graph 2 cos 4 theta as well as r equals 1 on the calculator. My window is 0 to 2 pi on my thetas, and then just -3 to 3 for the x's and y's. And what I get is the rose curve with 8 leaves for this first equation, and then you can see the r equals 1 inside here. So I'm just going to make a quick sketch of that. And there we go. So the circle is r equals 1, and this rose curve is r equals 2 cos 4 theta. All right, there are a lot of pieces whose area I'm trying to find. I'm trying to find the area of the tips of all of those petals. So I'm definitely going to use some symmetry here. In fact, I'm actually going to use kind of a lot of symmetry. I'm only going to find the area of half of this first petal. That's it. Doubling it would give me the area of one petal, and then multiplying that by 8 would give me all of it. So I'm really going to take this as 16 times the double integral that gives me the area of that one little petal. All right, taking an integral to find an area, a double integral to find an area, we always integrate the function 1. I am going to do this in polar coordinates, so my dA will be r dr d theta. All right, I guess I drew that in kind of dark, so we'll have to imagine our radial spoke this time. I guess I can start to draw it, but kind of imagine. We enter our region here at r equal 1, and we exit it here through the rose curve, 2 cos 4 theta. To get the theta values, I'm starting right on the x-axis, so that would be theta equals 0. And then to figure out this theta value, where they intersect, I will set my r's equal to one another. That means that cos 4 theta is equal to 1/2. So once again, I'm going to take the inverse or arc cosine of both sides. And 4 theta would be equal to the inverse cosine of 1/2. In the first quadrant, that is pi over 3 again. I'm stuck on that same value today. So dividing by 4, theta is going to be pi over 12. And this is my big advantage of only finding that one little piece. I would have a lot of intersection points to find here if I really needed to do all of these separately. So thank goodness for the symmetry in this problem. All right, let's find our integral. We have 16 integral from 0 to pi 12ths. And I'm integrating just r, so that's going to give me 1/2 r squared from 1 to 2 cos 4 theta. D theta. I'm going to go ahead and just get rid of the 1/2 and the 16, just make that an 8. R squared, plugging in the upper value, would be 4 cos squared 4 theta, minus, plugging in the lower value, that's just 1. And let's see, when I did that integral, I got 3.826. And that does include the 8 as a multiplier. All right, that brings us to the end of section 13.3.